King me! It's like another win for Dad. Oh, hey there! I didn't hear you come in. How are you doing today? Hopefully by now you've developed all the basic concepts you need to do curve sketching. Now we've been dealing only with polynomial functions, which aren't too exciting. Today we're going to look at some examples of some more difficult functions and how we can use some steps from what we've learned to figure out what the graphs of any function looks like. So let's get to it.
So today we're going to summarize everything we know about curve sketching. So we call this an algorithm for curve sketching. So an algorithm, of course, being a set of steps you can follow to accomplish a task. And our task is going to be to determine what graphs must look like based on their equation. So let's go through each of these steps. By the way, all of the examples I'm doing today and all the notes that I have are available on our course webpage for you to look at as well. First step, determine any intercepts, and that's provided they're easy to calculate. We don't need to do any difficult algebra if x-intercepts don't fall in nice places on a curve. For example, finding the x-intercept of a cubic that doesn't factor is very difficult and not usually worthwhile. Step 2, determine the end behavior of the function. So that's the limit as x approaches both positive and negative infinity. If that value, if that's approaches a constant value, then that of course will give you a horizontal asymptote as well. Of course, polynomials don't have horizontal asymptotes, but other graphs might. Determine if any vertical asymptotes exist, and that's for functions that are rational functions as well. When the denominator is undefined at a certain value, that usually gives you a vertical asymptote. Step 4, use the first derivative to find all critical points. So of course you set the first derivative to 0 and solve. Find the second derivative and any locations where it is also 0. Use the information from step 4 and 5 to determine the location of all turning points, which are also local maximums or local minimums, and points of inflection. Now, depending on what happens in step 4 and 5, that's really going to change how step 6 works. And I'll show you with some examples exactly what I mean when I say that. And then finally, sketch the function. And that's basically it. So as I present you with each example, you are welcome. These are going to be the 3 examples we try, and then I've got 4 for you to try as well. These are quite long. Now the first one, we have done this many times before, so I am going to go through that one fairly quickly, but I want to show you how, using this simple example, how we can combine these steps together and use the second derivative test to determine where turning points are without needing to verify turning points by checking both sides of the point or anything like that. Okay, so let's get started on the first example and you will see what I mean. So our first example, a polynomial function, like I said, we're going to go through this one pretty quickly because we've done a lot of these now. Finding the intercepts, well, first of all, set x equal to 0 and you get the y-intercept of 0, 1. Okay, so this is our first step. It's not necessary to label the steps, 1, 2, 3, 4, 5, 6, 7, but for a lesson that kind of makes it easier to follow. We can also find x-intercepts by setting y equal to 0. Now notice with this how convenient this is that this factors by grouping. Okay, if we common factor the first 2 terms and we common factor the second 2 terms, then we're able to factor this and get the 2 x-intercepts of 1 and negative 1. If it didn't factor by grouping, you'd have to use the factor theorem, which we did last semester in grade 12 advanced functions, and that's not really what we're looking for in calculus. Because the intercepts were easy to find here, I chose to include it in this example. So we have x-intercepts at 1, negative 1, and a y-intercept at 1 as well. Okay, end behavior. The end behavior of a polynomial function is determined by both whether it's an even or odd degree function and the leading coefficient. In this case, we get positive infinity and negative infinity. Okay, so that's step 1 and 2. Step 3, we said, was determine if any vertical asymptotes exist. Well, of course, here, that is, there are none. Step 4, finding the critical point. So that's where we take the derivative. Our derivative here is 3x squared minus 2x subtract 1. We set that to 0, okay, and this is a quadratic. You could use the quadratic formula if it didn't factor, but this one factors. We get critical points at x equals negative 1/3 and x equals 1. In my next step, I found the y values that correspond with those two critical points. One is 32/27 and the other one's at 0. I'm not showing the math for that because I'm sure you can do that, but those are our two critical points. Now, generally, you might be tempted to verify whether or not those critical points are in fact turning points or not. And I'm showing you this example to show you that that's not really necessary. We can instead move on to the second derivative. We want to find points of inflection anyway, so we want to know when the second derivative is equal to 0. So let's do that first, and we'll show why that's a good strategy to take. So I'm doing step 5, finding the second derivative. There's the first derivative, okay? And then if I take that derivative, I get 6x minus 2. I set that equal to 0, and I get x equals 1/3. Now the y value that goes with x equals 1/3 is 16/27. So I calculated that on my own. This tells us something really important. It tells us that we have our two critical points from above, that's these points up here. It tells us that they are in fact both turning points. And the reason they're both turning points is the second derivative is not 0. So if you remember our last lesson on second derivatives, we said if you have a critical point where the second derivative is not 0, then that critical point must be a turning point. And the reason being is that at that critical point, although the first derivative is 0, the second derivative is not. The rate of change is still changing, and hence the derivative is going to change sign. And that's a little complicated to understand. I hope I explained that okay. So we know that they're both turning points. We know that the second derivative is not 0 at negative 1/3 and 1 because we found here where the second derivative is 0. It's only 0 at x equals 1/3. So it would have been really unlucky if one of our critical points happened to be at x equals 1/3 because then, well, the second derivative wouldn't tell us for sure that that's a turning point. So we know they're both turning points, and then we know that this point here, since the first derivative is not equal to 0, it must be a point of inflection. And that is enough information that I can graph. Here's the graph with all the points we found labeled. Of course, there's our intercepts. Okay, and right there is our, one of them was a turning point. We verified that this is a turning point and this is a point of inflection. Now, I know that many of you know when polynomial functions have double roots, that those are also turning points. That only applies to polynomial functions. So we don't really talk about that in calculus because we're going to look at other functions where we have to use derivatives to figure out exactly where turning points are. Notice as well, although this here is not necessary, it might be useful had this been a harder example. Look at 1, 0. Look at the second derivative. The second derivative is 4, meaning the graph is concave up, greater than 0, and sure enough, we have a local min. The second derivative at x equals 1/3 is equal to negative 4, which is less than 0. So the graph is concave down, and sure enough, we have a local max. Remember, when your second derivative is less than 0, it means you are at a concave down portion of the curve. And if your second derivative is greater than 0, you're at a concave up portion of the curve. And hence, any critical points that belong to a concave up or a concave down section of the curve must also be turning points. Okay, so that was the first example. I'm going to move to the second one. Now the second example, let's just bring it up here again. So our second example, f of x equals x squared plus 1. Quite a bit more interesting. Finally, something that's not a polynomial function. So let's take a look at this. As you remember, hopefully, in grade 12 advanced functions last semester, we did work with functions kind of like this. We had some different strategies we had for determining what rational functions look like. So we might use some of those today as well. Now, if you like, it's not a bad idea to actually try this one on your own first. See if you can get it. I'm going to go through it with you. Some of the calculations and the algebra is a little bit long. It's easy to make a mistake. If you want to try this on your own first and see if you can figure out what this graph looks like, then by all means, pause the video and try it, and then come back and see. I'll leave that up to you. Okay, example 2. X over x squared plus 1. So first thing, finding the intercepts, pretty easy here. If you set x equal to 0, you get 0, and that's the only intercept. It goes to the origin, 0, 0. Okay, the end behavior is obviously a little bit more complicated here, so let's just take a look. The limit as x approaches positive infinity. Okay, So when I look at this, the first thing I see is that the positive 1 here is pretty insignificant. Okay? As x gets really big, that doesn't do much. So I can kind of ignore that and see that x over x squared is what's important. And in fact, that simplifies to 1 over x. Well, as x gets really, really big, 1 over x just gets closer and closer to 0. So that's why this graph approaches 0. Another thing that works is, look, the denominator has a higher degree than the numerator. When rational functions do that, it always means they're going to get closer and closer to 0. Imagine subbing in a very large number, like 100, for example. Okay? 100 is nothing compared to 100 squared, which is, of course, what, 10,000. So in this case, you would have 100 over 10,001, and the bigger and bigger x got, the more the closer this would get to 0, as this denominator just becomes so much bigger than the numerator. Now, the reason it's 0 from above is because 0 is a nice number. If you're above 0, it means you're positive, and if you're below 0, it means you're negative. Well, as you sub in big positive numbers here, obviously you have a positive divided by a positive, which is going to give you a positive number. As x approaches negative infinity, it's the same kind of rationale as over here, okay? However, now you're subbing in big negative numbers. So you have a large negative divided by a much larger positive number, because when you square a negative, you get a positive. So this ends up being a negative divided by a positive, which is negative. So although it gets closer and closer to 0, it's a negative number. So it's 0 from below. Okay, so there's step 2. Step 3, looking for vertical asymptotes. Now this one has no vertical asymptotes because x squared plus 1 cannot equal 0. So we don't have to worry about the denominator, any restrictions in the denominator. Okay, moving on to the derivative. Using the quotient rule here, just check that, should make sense with you. Simplifying gives me this right here. When is that equal to 0? Well, the denominator can never be 0, so we need to worry about that. When is f prime of x equal to 0? When negative x squared plus 1 equals 0, x squared equals 1, x is plus or minus 1. Okay, now if you plug in x equals 1, you'll get a half. If you plug in x equals negative 1, you'll get negative a half. And so those are our 2 critical points. Okay, 1, 1/2, and negative 1, negative 1/2. Now that wasn't a coincidence that it worked out that way. Look at this graph. Take a look at its equation again. X divided by x squared plus 1. That's actually an odd function. Not an odd degree function, but an odd function. No matter what, whether you plug in a positive or a negative, it doesn't matter for x squared. You'll always get a positive number. And for x, of course, it does make a difference. So let's think about, for example, plugging in the number 5. You'd have a 5 here, and you'd have a 5 squared here, which is 25. You get 5 over 26. Now imagine plugging in negative 5. Well, if you plug in negative 5 down here, you're still going to get 26, because negative 5 squared is 25. But now you're going to have negative 5 divided by 26. So this is an odd function. If you take an x value and you change it from positive to negative, you get the same y value also switched from positive to negative. So we're going to find that this always happens. Whatever x equals 1 produces a half, we know x equals negative 1 produces negative a half. The second derivative. Okay, this is where the algebra gets a little bit more complicated. So there's what I get when I use the quotient rule with the first derivative. In my next step, I just chose to clean up a couple things here. I took the 2x and the 2, multiplied them together to get a 4x. And now what I did in this step right here is I noticed that x squared plus 1 is a common factor, and so is 2x. So I factored all that stuff out here. And what I was left with, well, when you take this and you divide it by x squared plus 1, you get x squared plus 1. Okay? The x squared plus 1 here was factored out, and I'm just left with a 2 here now, and the negative x squared plus 1. So that's actually from here to here, we're just factoring. I cleaned up what's in these brackets here, okay, to produce negative x squared plus 3. And then also notice that, look, x squared plus 1 can now be divided off the top and bottom of this rational expression. In fact, you could have done that right up here if you saw that as well. And so here's what I get. F double prime of x equals negative 2x times negative x squared plus 3 over x squared plus 1 cubed. When is that equal to 0? Well, a rational expression is 0 when its numerator is 0. So that either happens when x equals 0, makes this factor 0, or when negative x squared plus 3 equals 0, which means x squared equals 3, which means x equals plus or minus root 3. So we have 3 critical points. And here are their corresponding y values. Sorry, pardon me. Those are not critical points. Those are points when the second derivative is equal to 0. Okay, the second derivative is equal to 0. Now notice our critical points were at 1 and negative 1, which is wonderful because we know that these must be turning points. Why? Because the second derivative was not equal to 0 at those points. Why is the second derivative not equal to 0 at those points? Because the second derivative is equal to 0 at x equals 0, x equals root 3, and x equals negative root 3, and neither of those numbers was 1 or negative 1. So we've determined that our first 2 critical points are turning points, and that our last 3 points must be points of inflection. So look at that. 2 turning points, 3 points of inflection. If we put all that together, we can actually come up with the only possibility for this graph. Now, if you're wondering how I did this, I started with 0, 0, and then these points I knew were turning points, so I graphed those next. And then it was pretty easy to get the rest of the graph because I knew the graph had to approach 0 from above here and 0 from below here. And sure enough, how could you have a local maximum here and not have a point of inflection, right? The curve is concave down, but it can't approach the asymptote without changing concavity. And the opposite thing is true over here as well. Now, I'd like to point out something that I also think is really important. If you were to look at f double prime of 1, what would you find? Well, notice this is concave down. That would mean that the second derivative must be less than 0. It also tells me that x equals 1. Since it's a critical point, and this is true, that I know for sure it's a local max. Now, I didn't need to check that. I could tell from one of my points being 0, 0, and from my end behavior and this point of inflection, I could tell that, look, this has to be a local max. And the same thing over here. There's no doubt that this is a local min. However, if I really wanted to be sure, I could look at the second derivative, plug in x equals negative 1, and I guarantee you get a number larger than 0, meaning this critical point is part of a portion of the curve that's concave up, and therefore is a local min. So although I didn't need to do this, you certainly could do that if you want, and I think it's just something you should understand. Now, how do you do f double prime of negative 1? Well, you go back to that big ugly equation, which is right here. There it is simplified, and you simply plug in negative 1, and you'll find that you get what I just said. Okay, so there we go. There's our second example. Let's try one more. So on to our last example. Like I said earlier, if you want, it might not be a bad idea to try this one on your own first before checking the solution, but I'll leave that up to you. X cubed divided by x cubed plus 1, another rational function. So the only intercept is f of 0 equals 0. If you plug in x equals 0, that's what you get. It's the only x or y intercept, so this one goes to the origin. Okay, let's look at the end behavior next. The limit as x approaches positive infinity. Okay, so just like the last example, we want to look at what terms are significant here. Notice again the plus 1. The plus 1 isn't really significant here. So this behaves, as x gets very large, this starts to behave more like x cubed over x cubed, which is just 1. So this approaches 1. Whether that's from positive or negative infinity, doesn't matter. So that means that y equals 1 is a horizontal asymptote. Okay, when you approach a constant value, you get that horizontal asymptote. Now, I think in the last example, I forgot to mention that y equals 0 was a horizontal asymptote. Here it's y equals 1. Now, why is it 1 from below? Okay, well, if we look at this, the plus 1 is what makes it 1 from below. So as x gets very, very large, So for example, when you plug in even x equals 10, 10 cubed is 1,000. So you get 1,000 divided by 1,001, which is a number that's slightly less than 1, because here the numerator will always be a little bit smaller than the denominator. Don't forget, when you're doing end behavior, you can always sub in large values to check and make sure that you're correct. Now, how about when x approaches negative infinity? Things are a little different now because we have negative numbers. So if you imagine plugging in negative 10 again, you're going to get negative 1,000 on the top. And on the bottom, you're going to get negative 1,000. But then you're going to add 1 to give you negative 999. So you have two very large negative numbers. So a large negative divided by a large negative, which does give you a positive value. But since your large, the larger negative is on the top, so like negative 1,000 divided by negative 999, you're always going to get a number a little bit bigger than 1. So in this case, it's 1 from above. Again, plugging in large values of x will help you see that. There is a vertical asymptote at x equals negative 1. That's because x cubed plus 1 is undefined. For x equals negative 1, you get 0 there in the denominator, so that gives you that vertical asymptote. Okay, on to our derivatives. Okay, using the quotient rule to do the first derivative here. Cleaning it up, we get 3x squared over x cubed plus 1 squared. And the derivative is 0 when x equals 0, because the numerator of 3x squared equals 0 for x equals 0 only. That's the only critical point at 0, 0. Let's take a look at the second derivative. Again, the algebra does get a little challenging here, but you find if you practice this, it looks a lot like example 2, and a lot of these kind of work out the same. So here's this is just the first line using the quotient rule, taking this derivative to get the second derivative. That's what our quotient rule looks like. Okay, cleaning it up a little bit. So the first thing I did here, is just to multiply 3x squared by 2 by 3x squared, and end up with 18x to the power of 4. And then again, notice I've got a common factor. I'm subtracting two things. 6x is a common factor, so I've got it down here. But so is x cubed plus 1. I've got x cubed plus 1 squared and x cubed plus 1. It's kind of like if you had y squared and y. Y would become a common factor. Well, in this case, your y is just x cubed plus 1. So I factored that out. So then I take this amount, I divide it out of this, and I'm left with just x cubed plus 1. And then I'm left with negative 3x cubed. Okay? Simplifying that gives me my final second derivative right here. Okay, 6x times 1 minus 2x cubed all over x cubed plus 1 to cube. By the way, this x cubed plus 1 and this x cubed plus 1, those divide out. So I'm divide the top and bottom to get rid of those. All right, well, when does f double prime of x equals 0? Well, at x equals 0, because 6x equals 0, or when, like I'm basically getting this line from looking at when is 6x times 1 minus 2x cubed, when is that equal to 0? Well, since it's factored, it's either when 6x equals 0, which happens when x equals 0, or when 1 minus 2x cubed equals 0. Solving that gives me 2x cubed equals 1, x cubed equals a half, x is the cubed root of 1/2. Now you can cube the top of that. The cubed root of 1 is still 1, and I get the cubed root of 2 here. I'm going to say that's about 0.8. I'm not sure off the top of my head, but I've got that down below. If you plug in x equals 1 over the cube root of 2 into the original function, you can do that because x cubed equals a half. So the original function was x cubed divided by x cubed plus 1. So I just plug in a half for x cubed and a half for x cubed, and I get 1 over 3/2, which gives me a third. And so there we go. Okay, so what did I find here? Well, one really nice thing happened. I know that this last point is a point of inflection. But notice how we kind of got unlucky. One of my critical points was at x equals 0. In fact, that's my only critical point, 0, 0. When I went to do the second derivative, I found that the second derivative was also 0 at x equals 0. So the first and second derivatives are both 0. So I don't know for sure that 0, 0 is a turning point. It could be a turning point. It could be a point of inflection. I don't know. If the second derivative at x equals 0 was positive, I'd know the graph is concave up and I have a min. If it were negative, I'd know it's concave down and I have a max, but I don't have either, so I don't know what's going on. However, I don't have the same problem with this point here. This point must be an inflection point since the first derivative wasn't 0. Okay, so for the graph, I haven't completed this graph yet. Instead, I said, okay, how do we do this? Well, let's do a few things. Let's plot our vertical and horizontal asymptotes. We start with that. Let's plot our point 0, 0 and our 1 point of inflection that we found above. So that's that 1 over the cubed root of 2. And let's graph what we can. Well, I know the end behavior of the function as it approaches 1 from below. Notice that I'm approaching it concave down. That's the only way to approach an asymptote from below. You try to draw it concave up, you just can't get it right. So I know that if this section here is concave down, and this is an inflection point, then this must be concave up. Now, I don't know what happens at 0, 0, so I'll leave that for now. I also know my end behavior over here, that approaches 1 from below, or sorry, from above. Okay. I also know that over here there are no points of inflection, there are no turning points, there are no other x-intercepts. So I really only have one choice for what this part of the curve looks like. It must look like that right there. Okay, pardon my messy writing there. It's hard to draw on this sometimes. Okay, now how about this portion of the graph is what's missing. I know there's either a turning point or a point of inflection here. I do know that if I drew a tangent line at this point, its slope would have to be 0. Since f prime of 0 is equal to 0, that doesn't mean you have a turning point necessarily, but it means you do have a horizontal tangent. Now, it's not that hard to figure out what's going on. If you plug in a number between 0 and -1, you're either going to get a positive value or a negative value. If it's a positive value, that means that this is a turning point and it does this right here. If it's a negative value, that means it doesn't turn, it must be a point of inflection. If you do that math, you'll find you do in fact get the point of inflection. You do get a negative value when you plug in x equals -1/2 into the original equation. And so this does this right here. Okay. Now, if you're wondering, and that's what that graph looks like, if you want to put that in Desmos, you can. You'll obviously get a bit better of a picture of it, but that's pretty much what you'll see. And you might also be wondering, hey, Mr. Elliott, maybe it can't be a turning point because it can't cross through the horizontal asymptote. That's not a rule. Graphs can cross through horizontal asymptotes. In general, they can't cross through vertical asymptotes, but they can cross through horizontal asymptotes. As it turns out, this one doesn't. I mean, the original equation was y equals x cubed divided by x cubed plus 1. There's no way to make that y value equal to 1. X cubed can never be the same as x cubed plus 1. It's just not possible. And so, in fact, it does not go that way. It does, in fact, go this way. So that's my last example. It's your job to work on these 4 examples right here. Now, I'm going to suggest that you do those and you use Desmos to help you out to make sure that you've got you've found the correct things, and odds are that's going to be enough for you. They're not short examples. They do take a little while. They're fairly lengthy, as you can see, and I hope you have some fun with them. I kind of treat it as a little game, trying to figure out what a graph looks like, and I hope that you enjoyed this lesson. Thanks for listening. See you next time.